in this equation, we could see this in two different ways. One way we could look at it and see that this is a radical equation because we have a radical here, and we could go through the steps in the process for isolating that guy and using the power property. But I also want you to see that this is quadratic in nature. And here's why. You've got your constant here, right? This guy, if I were to say this, if I said that my u is the square root of x, okay, then that would mean that u squared is equal to what?
X.
Right, u squared would equal x, right? Now, what is, in case you don't see this, isn't the square root of x the same thing as x to the what power? It's going to be on your test. It's x to the 1/2. If I were to double 1/2, what do you get?
Squared. No, just kidding.
You get 1.
Yeah.
So you see that if you double this exponent, you get that guy. Look at the other examples that we've done today. The first one I had x to the 4th and x squared. If you double x squared, if you double the exponent on the x squared, you get 4. The last example that we had was this guy. This had an exponent of 1. If I double that, I get 2. And this guy inside is the same. You've got your constant. That makes it quadratic in nature. Yes?
So when do you know when to use it? Just whenever it looks complicated?
Well,
Or
when it looks
everything else fits?
when it looks like it's set up almost like a quadratic equation, you've got your constant at the end, you've got some variable expression here, and his square is right there.
That's the key.
That's what you're looking for things that are quadratic in nature.
Well, quadratic in nature, but it doesn't necessarily mean that you have to place that u.
It doesn't mean right. It doesn't mean that you have to use that u substitution. Like on the last problem,
How do you know when you
So if
use
it's
the
set
u?
up like a
on this last problem, I did not have to do a u substitution.
It was just too ugly.
It would have been
but it's
a lot
not.
easier to do that, but I didn't have to. So let me show you on this one. If I do a u substitution, then all of a sudden this guy becomes u squared minus 5u plus 6 is equal to 0. I don't have radicals to worry about. I have a nice equation that's quadratic, and I love things that are quadratic, don't you? How does this factor?
U minus 3, u minus 2.
U minus 3 times u minus 2 equals 0, so that means that u equals what?
3, 4, u equals 2.
Right, u equals 3 or u equals 2. Now, that's what it was for u. I need to go back to x. So what did u represent?
Square root of x.
That was the square root of x. So I know that the square root of x equals 3 or what?
2.
The square root of x equals 2. How do I get the x out of the square root?
Square root.
I'm going to use that power property. I'm going to square that. So if I square both sides here, what do I get?
And x equals 4.
X equals 9, or here, x equals 4. Now let me tell you something. This original equation is not a polynomial. The reason it's not a polynomial is because of the square root of x. So I can't look at this and say definitively I have so many answers. When this is a radical equation, I have to check to make sure that everything works out. If I plug in 9, does that work out when I go across here? Let's see. Well, it's kind of hard to keep everything on one page. If I check this, I have 9 minus 5 times, what's the square root of 9?
3.
3 plus 6. Let's see, that's 9.
Right, that works out. Equals 0.
9 minus 15 plus 6 does equal 0. Okay, that checks out. If I plug in 4, I get 4 minus 5 times the square root of 4, which is 2,
That works out.
plus 6, 4 minus 10, plus 6 is 0. Both of these answers check out. What if one of them checks out and the other one causes you to have a contradiction of sorts? What would you say it is?
Extraneous?
You would call it extraneous. So when it's radical, you've always got to check those answers. Always.